Today we're talking about the kinetic molecular theory, sometimes called KMT. And the reason we're talking about this is because this is essentially the theory that describes essentially why, gases behave the way they do. We do know between pressure, volume, temperature, and the number of particles, now that we've discovered moles, we know the relationship can be basically broken down into PV equals nRT. And we've called this formula the static formula. And we know that we have derived from this bunch of relationships PV over T equals PV over T. And this, of course, only works when the moles are constant. This is the combined gas law. So we've worked with these two basic formulas. Okay, more importantly, the most important one is this one, and it's often called the ideal, gas law formula. Although I like to call it static, you will hear ideal occurring in your questions. Now, what does that mean? An ideal gas law is based on the theory that gases are behaving in certain ways in order for these relationships that we've studied to be perfect. Do not forget, when we have volume and temperature, of course, that's Kelvin temperature, being graphed, we get that direct proportion. When we have pressure and volume being graphed, we get that inverse relationship. So all of these relationships that we've studied that built this formula are based upon this theory that gases are behaving ideally. And ideally means and explains essentially why these relationships are as they are. For instance, think about this. We know the volume is the space that gases take up. Think with me. Now, why does a gas take up space? Well, we know gas particles, whether it's an atom or a molecule, we'll just do dots. Temperature is the average kinetic energy, the motion. If I make the molecules go faster, increase their molecular speed, speed is motion, translational motion, gases will take up bigger space. So if I've got a balloon, that balloon will expand because, and that's an ugly balloon, but that balloon will expand because gases will move faster and collide with the container walls more. There will be a greater distance between gas molecules as the temperature increases. So as the temperature increases, that means the motion of the molecules increases, their speed, and of course the volume goes up. When I drop liquid nitrogen on the balloon decreases in size because now the molecules go slower and they'll have a smaller space. Remember, volume is space that these atoms take up. So the space they require is less. For the videos we just watched, if you take about a seat in a theater, the seats in the theater will be closer together at lower temperatures, whereas seats in a theater will be what? Farther away at higher temperatures. That's why we compare gases at the same temperature and pressure, so that we're comparing how many positions or how many atoms or molecules, particles can fit in a certain space. Now, for all of this to work, for us to calculate mathematically, to explain this, we have a theory. And the theory is based very simply on the idea that each one of these gas particles is moving independently of the others. Think with me. If I want to measure and calculate the volume that a gas will occupy under a certain pressure, certain number of molecules, and a certain temperature in Kelvin, using my universal gas constant, I will get and calculate that new volume. If the temperature is increased, as we just stated, the molecules move farther, and there'll be a bigger space for these gases to occupy. The balloon will be bigger, and we can calculate what that volume, new volume, will be as I increase the temperature. However, if these molecules are not independent, if they start to attract themselves, meaning instead of moving in a straight line independent, they start moving closer together because they're attracted, okay? And they're not truly independent particles. They start attracting each other. Then what happens is our volume that we were to calculate is not going to come out. It's actually going to be what? That volume is going to be smaller than we expect, okay? And also if we measure the pressure is going to be affected. So when we understand and look at volumes and calculate these things, we have to assume that these molecules are moving, okay, independently. All right, so let's take a look at a demonstration that really shows this. It's a very simple one, but it shows where molecules should be independent. And as the temperature decreases, watch how they start to attract. Okay, let's go there. So what I have here is a demonstrator, and start it now, and it's going to basically shake these beads, and this is a model. Okay, so I'm going to turn this on. Now right now these are liquids, or here we go. So now we have a container. So look at the pressure, look at the collisions creating a pressure. We see the molecules moving randomly. So we have a certain number of collisions over an area, pressure, and molecules are moving, gas molecules are colliding. Now I'm going to take this container away from the middle. So what I'm going to do is I'm going to make the volume get bigger, and we should understand this is Boyle's law. As the volume expands, the number of collisions is going to be less. We could calculate this if each one of these gas molecules is totally independent. So what we're going to do is I'm going to take this out, and you notice what happened to the number of collisions. Keeping the temperature constant, the number of collisions dropped. But wait a minute. Are they all acting independently? Am I getting all the collisions? And the answer is no. Some of these molecules are attracting each other. So instead of going in a straight line motion and doing their own independent thing, they are attracting each other. They're acting non-ideal. The pressure that we are supposed to measure here is a lot less than we expected because of these molecules attracting the others. Okay, some of them are almost standing still. They're acting more like a little bit of a liquid. So we can't have gases do this. If they do, they're acting non-ideal. So to calculate the new pressure when the volume expands perfectly in our calculations, we can't have this attractive forces occur. If they do, our calculations are going to be off. And you know what? Our calculations are off because all gases have a little bit of what we call real gas behavior. Now I'm increasing the temperature. As I increase the temperature, what's happening to the attractive forces? And you can see that there's a lot less attractions as temperature goes up. So one way to make that real gas, that one was over here, where they were attracting, and make them act more what? Ideal, would be to increase the temperature. By giving these molecules more energy, they are overcoming these attractive forces. So I want you to see that this right here eventually, okay, is real gas behavior. This is how gases really behave, okay, when they attract each other. And we're gonna have deviations from our mathematics. This, okay, hopefully if I get this going, this maybe, when the temperature is higher, is more what? Ideal gas behavior. Well, now it's acting more ideal now, okay? But the point I'm trying to make here is that the higher temperatures, there's less attraction. So here is the more what? Ideal behavior, okay? So that's that demonstration. So if we were going to solve for the new pressure in that demonstration, remember PV equals nRT, we could use that. We could also use the combined gas law. But if I was going to solve for the new pressure when the volume drops, you could see from that demonstration that calculated pressure was going to be a lot larger than expected if the gases are attracting each other. There's going to be what? Less collisions. So in order for our calculations to work, our gases have to follow the kinetic molecular theory, which help us explain why they have these relationships. But these relationships only work if gases are acting ideally. And as I just said, There's no such thing as the ideal gas. We only have scenarios we can create more ideal behavior. In AP, we're going to study what we can do to these equations to match real gas behavior. But from this point forward, more like Regents chemistry, we've got to learn what are the postulates that make a gas act ideal so that these formulas work perfectly and there isn't some error. Now, the error is going to be small, but it's there, and we can limit that and understand that. So let's go through that. Now, understand that the reasoning I'm talking about this now is because we have a way to see who is the most ideal gas and who is the most real gas using our mole concepts, and we'll get to that. So let's get to what the postulates are, the requirements in order to a gas to be fully ideal and have and minimize any error. Okay, so what are the set of conditions that will make a gas act ideal and thus make my gas laws be calculated perfectly? Well, as you probably would understand, number one is that the gases have to be random. They have to do their own independent motion. Now, I like to use an analogy to help us remember these postulates, these basic postulates. And I like to think of the ideal gas as the ideal student. Now, ideal students like ideal gases don't really exist. Think of a student that runs from their last class to their next class, and they stay late in their last class to ask questions, and they want to be the first to get to the new class. They would have to move very, very what? Fast. Now, because they carry extra books in all their books, they got this big backpack and they're following. So they're running and racing from one class to the other. Okay. Now, when they do that, they are going to collide with other people. And when they do, they bounce off fast and keep going. People say, hey, what's going on? They bounce. Normally, when people collide into other people, they say, oh, I'm sorry. I'll help you pick that up. These individuals will bounce into people with their big backpacks and they'll just keep going and you bounce off, kind of like an 8-ball or a cue ball, and if you play pool, hits an 8-ball and they bounce off. So one molecule will hit another and these guys will bounce off, but the total energy is conserved. And we call these collisions elastic, like an elastic band, because they snap off. One will hit the other and then the other one will slow down, but the total energy is conserved. They don't stick together when they collide because they don't really have what we would say very important social skills. Think about that. Now, when they get to class, they sit down, lick their pencils, and they're ready for the teacher. And they're looking at the teacher, and they're looking at the teacher and trying to breathe the same pattern as the teacher, blink as the same pattern as the teacher, so that they don't miss a thing. They look at their teacher like a peregrine falcon would look at their prey. It's crazy, okay? Now, because they're so focused on the teacher, when another student asks them, hey, Ben, can I borrow a pencil? They say, I like turtles. And they're random in their response because they're so focused on the teacher. As you can see, they have very poor social skills. I'm not naming any people. I wasn't like, I'm in any case. So, they're random. Now, if you ask this student to go get the worksheets on the printer, they're upset for a second, but what they do is the printer's over here, they go in a straight line motion and they fly back so they don't miss anything. So again, they're fast and they go in a what? Straight line motion because they're random and they don't care about the others around them. So that's important. You think about ideal gases in the calculations, each gas has to do their own independent what? Random event to make the balloon expand as calculated or the pressure increase as calculated as the demo showed you. So my friends in chemistry, okay, that is one of the two things. Now, the fourth thing that I'll bring up, which is the most important, you can have People Magazine's most beautiful person, 2000, I don't know, 15 to the left of that person. People Magazine's most beautiful person, 2016 to the right of them. I don't know what happened to the 2015 person. They must have a bad year. But you can have the most beautiful people in the world to the left and to the right of this person, and they will have absolutely no attractions to them on top of the no social skills for this ideal student. Remember, ideal means it really doesn't exist. They have no attractions because they're so focused on their learning. They have no attractions. That's the reason why they went in a straight line motion. Now, why were they so fast? It just so happens that gases that move faster tend to have less attractions, just like you saw in the what? The demo. You go faster, molecules don't have time to attract. So the reason why they're random and they have no attractions is that they're fast. And the reason why they're fast is they have very, very small volumes. Now, that means the gases are the what? The lightest. Now, it also means because they go so fast, the space between molecules, we'll call this mean free path in AP chemistry, the space between them is so large compared to the space these volumes actually take up. So what they say is the volume is insignificant. You'll hear that. Significant means that their own space that they take up, their own volume, okay, is insignificant compared to the space they fly in. But you can also think of it as them being the lightest. And this is key because how do we know which gases are the lightest? Well, I can go to the what? My periodic table, and I can look at the what? The relative atomic mass of elements. This is what? 4 atomic mass units? The top number tells me it's what? 4 grams per mole, right? If I've got hydrogen, who is independently, if we get this 2 here, it's 1 gram per mole, but hydrogen's diatomic, it's a Hofbrinkel, so there's 2 of them. So this would equal, because it's really H2, this is equal to 2 grams per mole. And what's that mole? That's the number of particles that fills a box that's 22.4 liters at standard temperature and pressure. Who's a lighter gas? What does this mean? This means that hydrogen, okay, as a diatomic molecule is half the mass as the monoatomic molecule of helium. So this is a lighter gas molecule, which means it's faster, which means it has less attractions, which means it's more ideal. So you can see, we can use our mole concept to see which gases are more ideal just based upon their individual what? Their individual masses. Okay, now we should use the molecular mass just like I did for H2, but some gases are monoatomic. So that's an important idea that we're reaching for in the mole concept to help us with that. All right, now let's deal with the real gas. The real gas gets to what? Gets to the class barely on time, is moving slower. Okay, so why is it moving slower? Well, because these guys have bigger volumes, meaning they're heavier, which could also mean the space between molecules is closer. Why? Because they have attractions, as we just saw. They have attractions. Think of real gases really have attractions between molecules. We'll talk about what those attractions are. You learned in AP Bio, one type of attraction is H bonding. It's not a bond, it's an attraction between molecules. Because they have attractions, they're not random, meaning if you ask them to get the worksheets from the printer, a real gas is not going to go straight. It's going to go where its friends are in the other class and say, hey, what's up? How you doing? High five. And then you eventually come back, and then they'll do what? The long way back. And you would say that their paths are not random, they're curved. And it takes longer for them to get to the container wall. Therefore, their pressure, okay, that they produce is a lot less than expected. And our what? Formulas we're calculating for have deviation. Okay, now they don't move as fast, but when they do collide, their collisions are inelastic. What does that mean? Well, that means when they collide, like for instance, someone collides, they actually have the social skills because they have attraction, maybe too much, okay? They collide with you in the hallway and say, hey, how you doing? What's going on? Give me the digits, hey. They collide and they stick together. In fact, you're trying to move away from them and they're probably like following you a little bit Because they what? They have attraction, which means what? Which means they're not random. They don't move independently, which means you can't expect anything you're calculating here to come out perfectly. It's truth be known that all gases have real behavior, okay? But we do have gases that are more what? Ideal. I should do another bad color. We do have some gases that are more real than others because they're heavier. And we have ones that are what? More ideal because they're lighter. Okay? Now, besides looking at either their atomic masses or their densities, density gives you the mass per volume, right? Well, if the volume is going to be the same for two gases, then of course the one with the greater mass, higher density, is going to be a more real gas, okay? So that's how we deal with that. Now, very simply, we often talk about how I can make a real gas into an ideal gas, okay? So let's talk about an ideal gas. Let's talk about a real gas that has these problems because of attractions. I want them to have less attractions. So how can I make a real gas into ideal gas? And I'm going to use two values, pressure and temperature. Well, we just saw from the what? From the demonstration that if I increase the temperature, there's less time to have attractions. They're going to go faster. They're going to be less random. Less not random, I should say, and more random and going faster and moving in straight lines. So increasing the temperature makes a real gas. I like to visualize as real gases close to each other. Okay, they're attracting. And then ideal gases are farther away. That's space between, as Dave Matthews would say. Okay, there's a space there. So how do I go from attractions? Increase the temperature, make them move more. They're going to be farther away and have less attractions, and they're going to act more ideal and closer to the calculated result. What do I do with pressure? Don't forget, pressure is going to be the force of other molecules slamming into them. So you've got a lot of pressure keeping them close. Wouldn't it make sense to decrease the pressure so that there's less collisions on these molecules so that they can be far apart? And that's lowering the pressure independently. Don't think that these are tied together. And raising the temperature independently will create the ideal gas behavior. Okay? And of course, going from ideal, how do I make an ideal real? It's the opposite. I'm going to use pressure and temperature. Again, these are independent values. And I would lower the temperature. Hey, how can I make a gas who's by itself attract each other? Lower the temperature. Hey, do we know about something like this? If you lower the temperature of the gas, will it eventually condense into a liquid? Didn't we learn about cooling curves? It's all interconnected, party people. Remember this? Gas to a liquid, gas going to a liquid is going to condense. We know gases become liquids when you lower the temperature, so you make them more real by lowering the temperature. And of course, if you want them together, you're going to increase the pressure, okay? So these are really, really important, but if you use the analogy ideal versus real, I think this could really help. Now, one last piece of topic that we're going to talk about is how fast these molecules diffuse or effuse. Now, diffuse and effuse really are the same thing. Diffuse means how well does a gas, how well does a gas, I'm not sure what happened there. So talking about diffuse, how well does a gas escape into a room? So let's say you have a bottle of perfume here. It's an ugly bottle, but hey, I'm tall. And the liquid has a vapor pressure, right? It's evaporating into a gas, and then it spreads. How fast will it fill a room? Well, how fast a gas what? Moves, which is based upon its speed. And what you should know is gases that are lighter move more, move faster. Yes? My gosh. Okay, think about this. Kinetic energy, which we're going to learn, is equal to 1/2 the mass times its speed, velocity squared. So if the kinetic energy is the same for two gases, the overall motion energy the same for two gases, make this the red gas, okay? So these numbers are the same. Okay, so they have to equal each other. All right, if we have a higher mass for the blue, this is a bigger gas molecule, it's more real, and then I have a smaller gas molecule for the red. So if the mass is bigger, okay, the kinetic energy is the same for both. They're at the same temperature, all right? Same temperature is the same average kinetic energy. So if they're the same temperature, if the mass goes up, the velocity has to drop. If the mass is lower, this being the same, the velocity has to increase, the speed. Remember, these are inverse relationships. So at the same temperature, a bigger molecule goes slower, a lighter one goes faster. So who's going to mix into the room faster? The lighter gas. This is called Graham's law of diffusion. Now the word effusion is mixing through a hole. Okay, so let's look at a demonstration of this. So I've got my larger gas molecule which moves slower and a smaller gas molecule which moves faster. Right now they're at absolute zero, not moving. So we're going to turn on the molecular mass demonstrator at some point here. And at some point here, I'm going to put in a barrier that shows how the smaller ones, because they're going to move faster, get through the opening. Okay, so even though my video is dropping in its quality, you can see that the lighter ones, here we go, the lighter ones are going faster. Now I'm going to put in a barrier or a slit. So I'm moving this to the side. I'm going to put in a slit, and you should see that the little hole, that's the hole there that both can fit through. What do you expect? Now, diffusion is mixing into the room. Effusion means that you're going to go through a small opening. It's the same idea, though. Who's going to get to the opening faster? The heavier, slower moving gas molecules or the lighter ones? Okay, at some point, I'm going to turn this on, and you can see that the lighter ones are what? Getting to that position better than the what? The bigger ones. And we can see that there's effusion, or a movement of light, faster gas to a heavier gas. And this is one way we separate gases, but this is the law of effusion. It's the idea based upon lighter gases move faster. How do I find that? I can go right to my periodic table like I showed you. So the gases that move faster or more what? Ideal or real? They are more ideal. And they will diffuse faster because of that. And I can, again, to figure this out, all I do is go to I can look at densities, or I can look at what? Atomic masses, or I can do a formula or molecular mass to find out.